So welcome everybody, good afternoon. I don't know if you remember, but some weeks ago we announced that the next seminar would be Dr. Ryan DeFever. We had to postpone that, but today is finally the day that we welcome here. So welcome Dr. Ryan DeFever. He received his bachelor degree in 2014 and his Ph.D. in chemical engineering from Clemson University in 2019. His doctoral research was performed under the guidance of Professor Sapna Sarupría and largely focused on crystal nucleation and the development and implementation of rare event sampling algorithms. Since September 2019, he has been a postdoctoral research associate with Professor Edward Maginn at the University of Notre Dame. In the time, he has been responsible for the development of molecular simulation design framework Cassandra, used polarizable models to study the dynamics and thermodynamics of molten salts, and a machine learning directed force field development framework. His currently research interest lies at the interface of methods development, software development, and application thereof to solve challenging problems with environmental implications. So once again, welcome Dr. Ryan DeFever. The stage is yours, about virtual.
Thank you so much. Okay, let's see if we can get this going here. Can everyone see that?
Yes.
Great. Okay, so thank you so much for the kind introduction and thank you for the opportunity to speak here today. I'm really excited to be here. Today I'm going to be talking about a couple different projects I've been working on over the last year and a half or so, both of which I think fall under the umbrella of really thinking about the tools that we need for the next generation of molecular simulations. And this is automated reproducible simulation workflows and then better methods to develop force fields for specific molecules where we don't have accurate force fields at the moment. So I'm going to motivate this by starting out and talking about some trends that I see transforming engineering, science, and frankly, society. And the first one is automation. So this is a picture of a facility that's about 2 hours north of here. And what this company does is they build assembly lines that are fully automated. So if you're interested in automating the manufacturing of some product, you might go to this company and say, okay, here's what I need to build. And they'll say, here's the robots you need. We'll put it all together. We'll manufacture it, design the controls, and we'll put it on your floor. And if you ever have the opportunity to see one of these facilities in person, I strongly encourage you to do so. They're absolutely incredible facilities. And having been to them a couple times, what I'm here to tell you is that automation is not coming, it's fully here. And along those lines, the McKinsey Global Institute put out a report a couple years back that showed that 50% of the total working hours in the United States were automatable with currently existing technologies. And some of that, of course, was physical labor, like, for example, assembling different products. But some of that's also data processing and data collection. So this is a large fraction of our existing labor that can and will be automated away. The second trend that you see that everyone is talking about is machine learning. And in some ways, I think that we tend to think this is a little bit oversold because especially most of us here probably are well aware that artificial intelligence and machine learning really are very advanced statistical techniques that are being applied to solve very specific problems. But even though that's the case, deploying these technologies on a broad scale is having a really large impact globally. Estimated $5 trillion in annual value, which is a quite large number when you consider that the global GDP is around $80 trillion a year. And then the third trend that I see having a large impact is computing. And this one we're all a little bit more familiar with. Here on the left, I'm showing the supercomputing power of the largest supercomputer in the world for over the last 3 decades. So this is a log scale here. And one thing I'd like to point out, other than just the absolutely phenomenal growth, is that if you look in 2014, I started my PhD work, compared to today, the world's largest supercomputer has more than 10 times the power it did. So this growth is really, really phenomenal. And if you look at the efficiency of computing, so if you look at the amount of energy it takes for a single unit of computing, that's decreasing exponentially as well. And this is really important because the the energy consumption per unit of computing is effectively the marginal cost that you have for running an extra unit of computation. So the point here is that we have a lot of computing power today, and we almost can't fathom the amount of computing power that we're going to have in another 1 or 2 decades. So these 3 trends are, of course, not independent. They're evolving together. The computing power that we have is enabling us to build really complex machine learning models that we wouldn't have been able to train only a decade ago. And these machine learning models are, of course, enabling advances in automation, both in the physical domain with things like computer vision, but also in the virtual domain when you think about data processing and data analysis. Now, next, I'd like to think about, what this means in terms of where we might have some opportunities to think about transforming engineering research. So I'm an engineer, so I'm going to frame this at an engineering level. And I've borrowed this very nice figure from a professor at the University of Notre Dame, Professor Dowling, who's a collaborator on some of our later work. And I really like it because it shows how you can connect the material scale or even the molecular scale through the device scale, the system scale, and all the way up to the global infrastructure scale. So as an engineer, I like to think about trying to solve problems at the systems and at the infrastructure scale. We want to solve CO2 sequestration, or we want to solve water shortages. These are the type of problems that we want to solve. But as someone who's been trained in what I would probably consider molecular engineering, I like to think about applying solutions at the material scale or even at the molecular scale. And so it's abundantly clear that one thing we're absolutely going to need is multi-scale models which help connect the material scale up to the device scale and up to the system scale. So this is something that I think is going to be really important. But the other thing that we need is the reason that we're really wanting to look at doing engineering at the material or at the molecular level is because we think the prospective design space is so large. And so we need good techniques to explore those design spaces. And a couple of the techniques that have been proposed are high throughput screening and inverse design. Now, the basic idea of high throughput screening is you synthesize a bunch of molecules or you simulate a bunch of molecules, you characterize the properties, and then you're just going to go and you're going to pick out the best. Inverse design takes kind of the opposite approach. So with inverse design, what you're going to do is specify the properties that you want ahead of time. Then you're going to have some model, and this is really the challenge of inverse design, that's going to tell you, okay, for this property, here's a molecule or material that will work. And then you're going to go synthesize and confirm that the prediction of the model was correct. Now, one thing I want to emphasize is that these 2 approaches are not as distinct as they might first appear. And this is because most inverse design approaches are going to require reasonably large data sets to train the model that's going to get you from desired property to molecular material. Oops, excuse me. Sorry about that. And most high throughput screening approaches, if you start to iterate on a high throughput screening approach or do this in a little bit more of an intelligent way, it's going to start to look very, very similar to an inverse design approach. So these 2 ideas are really ideas that can work together, and I don't think they're necessarily so distinct. Now, the next question you might ask is, well, where do molecular simulations fit in all this? And I'm sure most of us have seen a figure that looks, something like this before, but I like it because it shows how molecular simulations sit at this interface of theory, molecular modeling, this idea of a computer experiment and computing itself. Now, historically, and this is going to be a generalization, but I would argue that historically, molecular simulations have, in a large sense, been used to test theories by doing computer experiments, and also to gain insights into length and time scales that are really challenging to access experimentally. So I would consider this more of an explanatory regime. And where I want to go, what I think is really interesting for the future is moving into a predictive regime, where we're really talking about using simulations to predict the properties of materials that haven't been synthesized in the lab and helping to use simulations to guide basically what experiments you're going to do next. And so to do this, we really need to evolve from this more explanatory regime into the more predictive regime. I do want to point out, everything we've used simulations for historically is still very valuable, and that's going to, continue to be used going forward. But I'm really interested in this predictive aspect of simulations. So when we put these together, I see some really exciting opportunities for research in the future, thinking about high throughput screening of large design spaces, integrating molecular simulations with process modeling and design frameworks, and also even automated simulation execution where you have some machine learning framework that's basically picking what simulation is going to be run next. And some of this is being done today, but to make this happen at a larger scale, I think we need a little bit of simulation infrastructure to build up. And what I'm going to argue is a couple things we need. One, we need accurate force fields. If we don't have accurate force fields, our simulations are meaningless to experiments. We can't use them for experimental design. The second thing we need is automated simulation workflows. Most of what I'm proposing here going forward, combined with the just phenomenal amount of computing power we're going to have, means that we're no longer talking about running one-off simulations. We're going to be talking about running hundreds of simulations or thousands. In some cases, the simulations aren't going to be initiated by a user. It might be initiated by another software framework. So this needs to be completely automated start to finish. And I'm sure there's more that I'm not mentioning here, but these are two big pieces that I see that are important to work on. So with that, I'm going to move into the first part of my talk, which is focused on automated and reproducible molecular simulation workflows. This work was done in collaboration with some researchers at Vanderbilt University, Professor Cummings and a graduate student, Ray Matsumoto. Funding comes from the National Science Foundation. I want to acknowledge software development teams. I really built upon the work that previous developers had done on these projects. I wouldn't have been able to do this all by myself. So before I go any further, I want to define this idea of a workflow. So the definition is a sequence of processes through which a piece of work passes from initiation to completion. And I really want to focus on that idea of going all the way from initiation all the way to completion. So an automated workflow is one where you get start to finish with whatever set of simulation tasks you want to perform without any human intervention. And if it's reproducible, well, that just means that it's easy for someone else to come along and verify and reproduce what you've already done. So I've already motivated the automated aspect a little bit. So now I want to talk about the reproducible aspect. So why do we care about reproducibility? I don't think this is a hard sell. It's central to the scientific endeavor. Basically, when we have reproducible science, we get these positive benefits. The results accessible to anyone who has the knowledge and resource to carry out the experiment. You can modify the original experiment slightly to establish how robust the original result was. And when science isn't reproducible, we get negative side effects, incorrect results in the literature, poor graduate students or postdocs trying to reproduce results and not being able to because something was wrong originally. And eventually, public confidence in science is diminished. So, these are all bad things. Now, a fun question you can ask is, do you think publications in our field are reproducible? And Nature actually had this survey back in 2016. And so what they asked was what percentage of work people thought was reproducible in their field. And the way to look at this graph is the y-axis is the percentage of work that someone thought was reproducible, and the width of the bar is the number of people in the field that thought that percentage was reproducible. So in chemistry, physics, and engineering, people are largely pretty confident that, well over 70 or 80% of the literature in their field is reproducible. However, they asked a follow-up question that revealed a bit more of kind of the underbelly of this problem. And they basically said, have you ever failed to reproduce an experiment? And they broke down the responses into two categories: failed to reproduce my own experiment and failed to reproduce someone else's experiment. And what we see is even those very confident chemists, physicists, and engineers, over 50% of them have failed to reproduce one of their own experiment, and even more of them have failed to reproduce someone else's experiment. So whether or not we have a reproducibility crisis, I'm not trying to get into that argument, but I think this right here alone should tell you that we need to, kind of constantly be working on doing a little bit better and making sure the work we're doing is reproducible. So transitioning back to molecular simulations, what makes reproducibility difficult in molecular simulations? The challenges are going to be inherently domain specific, but I would argue broadly speaking, you can break them down into a few categories. Pre-simulation, this comes down to exactly how did you construct your system from the point that you sat down at your computer to the point that you had a system that you're inputting into a simulation for. What did you do? When you run the simulation, what parameters did you use? Force field options, input options. People are pretty good at reporting software versions. Most of the simulation engines these days we use are pretty well validated. So those are kind of lesser concerns. And then on the analysis side, what codes did you use? Oftentimes custom codes to perform analysis. And then, did you report your data in a way that was, faithful to what the data showed? And what I would argue is that each of these steps is becoming more difficult to do in a reproducible fashion, primarily because of the increasing complexity of the systems that we're studying and the necessarily increasing complexity of the computational workflows that we're using to study those systems. So back in the days when everyone was, well, not everyone, but the early members of our field were studying 128 Lennard-Jones spheres. It was pretty easy to specify what you started with, what you did, and what you got. But nowadays, if you're studying, a polymeric system or a system that has a surface with something grafted on it, you often have very complex construction, relaxation, and equilibration procedures. And these details are just inevitably almost impossible to report in full detail in the literature. So next, I'm going to argue that just sharing your codes and data is not enough. So this is a great first step. What I mean by this when I say sharing codes and data, I mean you complete the project, and then at the very end you say, oh, I want to make all this publicly available. So you kind of go scrounge around, you find the files you use, you scrape it all together, you put it all in one spot, you throw it on GitHub, and you add a little README. This is good. It's much better than nothing. I'm not going to bash it too much, but I think we can do a lot better than that. And the direction that I think we can go is I think we can build tools that make it easy to build reproducible workflows as we go as part of our day-to-day research. So it's not a post-hoc step. It's not an after-the-fact step. They're just the tools that we're using on a day-to-day basis. So to talk about that, I'm going to show how we've integrated Cassandra with MoSDeF to do reproducible Monte Carlo simulations. For those of you who aren't familiar, Cassandra is a software package for Monte Carlo of atomistic systems. It's been developed in the Maginn group over the last decade or so. And just, for rough sense of things, it's about 30,000 lines and it's written in Fortran. MoSDeF, on the other hand, is a Python-based framework. It helps users script the system construction and force field application steps of molecular simulations with the goal of making these steps easier to share and easier to reproduce. A little bit more detail just to give everyone a little bit of a more concrete sense of what we're talking about here. So two of the key packages in MoSDeF are mbuild and Foyer. mbuild allows you to do hierarchical system construction. So you can build these really complex systems piece by piece and then put them all together. And you can do all of this in Python. So mbuild is basically a library that helps make this easier to do. And then Foyer is a package for basically distributing and applying force field parameters to a system you've built in mbuild. So this is the goal of this is to make those steps more consistent and make it really easy to share the exact force field parameters you used, and also support more interoperability between different simulation engines, because once you have a system that you've parameterized in Foyer, you can save input files for different engines, all from the same starting point. So before we thought about integrating Cassandra with MoSDeF, we had this really phenomenal flow diagram in the 1.2 user manual for Cassandra of how you were supposed to set up a simulation in Cassandra. And I'm not going to go through all the steps here, but the main points that I want to make is there's several steps here that require edits by hand, and there's several steps here where you might use GUI-based software, both of which things we view as negative for reproducibility. Ultimately, to run a simulation in Cassandra, what we need is two input files, a molecular connectivity file, which is basically our force field information, and then an input file, which contains all the other parameters. So to get the molecular connectivity file, I'm not going to show you the behind the scenes nitty gritty, but I'm going to show you, how you generate one now. And the way you can generate one now is you can import mbuild and Foyer. Here we're creating a molecule. This is a three-dimensional structure that we're able to create just from the SMILE string here. So this is a dimethyl ether molecule. And then Foyer has some built-in support for force fields like OPLS all atom, although really the power of Foyer is that you can build your own force fields and then distribute them. But here we're just going to load in some parameters that they already have. We can apply the force field to the molecule we have, and then we can write an MCF file with a single line of code. So now, basically, we can get to an MCF file. We can cover all of these steps that I've covered in green, all with about 5 lines of Python. So that's a nice advancement. So the next thing we need to think about is the input file and how we can construct that. Just to give you an idea of what the Cassandra input file looks like, it's a pretty standard input file. You've got headings, you have different parameters you have to list out. They have to be in a certain order. This input file is normally generated by hand. you have a whole bunch of system-dependent selections, and where we'd like to go is generate this automatically. We'd like to offer some, good default options for a new user for Monte Carlo, and we want to interface this through MoSDeF with Python. When we sat down, we wanted to simplify this as much as possible, so we kind of made a big diagram of all the different parts of a Monte Carlo simulation and thought about how we could organize them into kind of a consistent logical flow. And what we came up with is these 3 steps. You first build the system. So the system is what you're going to simulate. It has your simulation boxes. It has your initial structure. It has your force field parameters. You then define your move set. So this is the different types of Monte Carlo moves you want to do, the probabilities of each of those moves, and the associated parameters. And then finally, you make some last runtime selections, like the temperature, the pressure, and how long you want to simulate. So this maps onto a really nice, simple workflow. And now, all it takes to run an NVT simulation in Cassandra is what I'm showing in front of you. This is start to finish, starting from nothing, no input files, and running an NVT Monte Carlo simulation in Cassandra. So this first part I've already shown. We create a molecule and apply the force field. You come down here, we define our system, we pass in our simulation boxes, what's in our simulation boxes, and then we create the move set, we specify an ensemble and what molecules we're simulating. This provides a default set of move probabilities. You can of course edit these, but here we're not choosing to do so. And then you say, mc.run, and you specify the last few things you need to run your simulation. When you do this mc.run step, this does everything needed to run Cassandra. It writes all your MCF files and your input files. It runs the fragment library generation, and it runs a Cassandra simulation. So this one function, start to finish, runs an NVT Monte Carlo simulation. So you say, great, okay, this is cool. You've built a nice Python interface around Cassandra. Why do I care? So what I'm going to argue, oh yeah, sorry, we've now basically, we can go start to finish all in one script. But why do you care? This is the important thing. The reason you care is because I'm going to argue this allows you to migrate to what I'm going to call function-based programming for molecular simulations. And the way I'm going to explain this is by walking through a simple example. So imagine we want to simulate this system here. So we have a graphene pore, and inside the pore we have some water and we have some salt. And let's imagine that we're interested in studying the properties of the fluid in the pore, and we have some design variables. So we're interested in looking at the pore width, we're interested in looking at the number of ion pairs in the pore, the number of water, and then maybe the type of the ions. So do we have sodium chloride or potassium chloride or sodium fluoride? So these are your kind of design variables. So when we move to a function-based programming model, what we can do then is we can use mbuild and we can write a function called create system. And what this function does, the arguments to this function are in fact basically your design variables. And what this function will do is it'll build this system for you and it'll return a fully constructed system. And so anytime you want to change one of these design variables, all you need to do is make a different call to this create system function. Likewise, what you can do is you can define a run simulation function. So this run simulation function is going to accept as one of its arguments your constructed system, and then a few other details. And in this case here, we're actually going to run 2 simulations sequentially. We're going to run an NVT Monte Carlo simulation followed by a grand canonical simulation. And all the details that are going to be the same for every simulation, for example, cutoffs, how you're going to handle the long-range electrostatics, anything that doesn't change can just go inside this one function. And so what that means is every time you call this function, you know you're going to get consistent behavior. You don't have to worry that you copied an input file and made a typo at some when you copied it incorrectly. So then when you go to actually run your simulation, all you have to do is define your selections, create the system by calling the create system function, and then run the simulations by calling the run simulation function. So I think this is a really powerful a way to think about performing molecular simulations, particularly when you think about moving towards high throughput screening or these sorts of automated frameworks. So this, of course, it has its pros and it has its cons. The benefits of this, it makes it really easy to initialize a large number of simulations. It lets the researcher focus on the experimental design more than focusing on the nitty-gritty every time. They can step back and think a little bit more broadly about what the experiment they're trying to run is. And it makes it possible to integrate this with unit testing frameworks. So all these functions are in Python. There's unit testing frameworks you can use in Python to validate that the behavior of the function is what you expect. Downsides, it does require some Python programming experience. Especially for a bigger workflow, this is going to take some time and effort to set up initially. You're not going to set this up in 2 minutes. And it also can make it easier for mistakes to go unnoticed. So the benefit that we get with enabling the researcher to focus on the experimental design comes from the fact that we're abstracting away some of the details. And the downside of abstracting away some of the details is that you're a little bit further removed from the simulation engine. And when you're a little bit further removed, it can make it easier for mistakes to go unnoticed. So this has pros and cons, but on the whole, I think this is the direction that we're going to have to go to support what I see as the type of simulations we want to run in the future. Now I want to show one more example briefly to kind of give you an idea of what can be done with this. So for this example, what we were doing is we wanted to say like, okay, we have this new software, what can we do with it? What's interesting? And we're chemical engineers, right? So we said, well, let's look at alkanes, because that's what chemical engineers always start with. And so we said, can we compute vapor liquid equilibria for all alkanes with 10 or less carbon atoms? So if you look at all the linear and branched alkanes with 10 or less carbon atoms, it comes out to 150 different molecules that you have, because the number of isomers starts to go up really quickly here as you increase the number of carbons. And so then what we're able to do is we're able to integrate MoSDeF Cassandra with Signac, which I strongly encourage everyone to look into if they're not familiar with Signac. It's a workflow management software. And what we can define is this Signac workflow, where in this workflow, each box is a function. So we can start from basically nothing, just calculating our initial box sizes, equilibrate a liquid with NPT Monte Carlo, equilibrate our Gibbs systems, and then we can calculate properties down here. And all of this can be defined ahead of time, and all of this can be run without any human intervention whatsoever. And so I'm just showing the results up here because it's kind of a fun set of results to visualize. So this is used the trap united atom force field. We're looking at the vapor pressure, and all these were run at the experimental normal boiling point. So if the vapor pressure matched experiment, they would all be right here at 1 bar. They of course have some slight deviations. But this gives you a sense of the type of problem you can do. And one thing I want to point out is, once again, this is 150 different molecules, not 150 different temperatures. Running simulations for one molecule at 150 temperatures would be a much simpler task. So I hope so far what I've shown you is that the challenge of doing reproducible simulations is really a workflow management challenge. And I really think that the way to go about this is to create tools that make it easy to build reproducible workflows as part of our day-to-day research. So if you're interested in finding out more, here's links for MoSDeF Cassandra, also MoSDeF and Signac. I won't stay here long, but please, if you try any of these out, give feedback. I'm really interested to see what other people think. Okay, so I started here. I've now talked about automated simulation workflows and what we can do to try to move in a direction of making that more accessible. The second thing I want to talk about is trying to develop more accurate force fields. And so the title for the second part of my talk is Machine Learning Directed Force Field Development. This work was done with co-authors from the University of Notre Dame, Professor Dowling, who is in the chemical engineering department as well, Bridget Beffert, who is a graduate student who is co-advised by Professor Maginn and Dowling. Her and I have worked closely together on this from the very beginning. And then Garrett Toe, who's a graduate student with Professor Maginn, who joined a little bit later on in the project to help apply our methodology to one of his systems. Funding, once again, comes from the National Science Foundation. So I want to start out with my molecular simulation in a nutshell slide. And so the basic idea that we have with molecular simulation is that we're going to take some model and we're going to take some simulation method. We're going to throw a bunch of computing power at it, and we're going to apply some tools from statistical mechanics, and then we're going to compute some properties. That's the basic idea. Now, the accuracy of these properties compared to experiment is going to be affected by two things. First, the accuracy of the model we're using. So how faithfully does the model we pick reproduce the physics of the system? And then are we able to sample the relevant length and timescales for the property that we're interested in computing? And these two things have a little bit of a trade-off. So the methods that are most faithful to the physics of the world are, ab initio quantum chemical methods, but these methods are limited to quite short length and timescales. As we move up the ladder, we start to get a little bit longer time scales and larger length scales, but we sacrifice a little bit of accuracy, if you will, or faithfulness to the underlying physics. Now, our focus is going to be on atomistic force field-based simulations and developing atomistic force fields. For us, the balance between the accuracy of length and time scales is quite nice. But this is not to say that these other methods aren't very, very valuable for different problems. It just turns out that for the problems we're interested in, this is our happy place. We really like these atomistic force field-based simulations. So thinking a little bit more about the force fields, what do they look like? So this is an example of a functional form. This is taken from GAF. So we have the potential energy here, U, written as a function of all the coordinates in the system, the vector R here. And this looks a bit ugly, but we can break this down into a few different components. So we have our intramolecular terms, bonds, angles, dihedrals. We then have a charge-charge term, and then we have a repulsion-dispersion term, which normally takes the form of a Lennard-Jones potential, or often does. Now, the challenge of developing or optimizing force fields is that there's a whole bunch of parameters that you can see here. So I've highlighted all the parameters. So in principle, we need to figure out what the values are for all of these different parameters. And there's a few different strategies that you can take for doing this. There's bottom-up strategies, where you use a quantum chemical method to compute some property that you're interested in, maybe a vibrational frequency or an equilibrium bond length, and then you fit the classical parameters to try to best reproduce the properties that you computed with the more accurate method. Alternatively, you can take a top-down approach where you start from experimental data, and then you try to figure out what force field parameters will yield a result which best reproduces that experimental data. Now, in general, we believe the intramolecular and the charge-charge terms can be relatively well defined from bottom-up methods. There's been a fair bit of work to develop approaches to get these quantities from bottom-up. But the repulsion and dispersion terms are much, much more difficult to do from bottom-up tuning. And so these generally are going to require a top-down approach to force field parameterization. As many of us know, over the years, there's been a lot of effort to develop off-the-shelf force fields, but unfortunately, these generic off-the-shelf force fields lack quantitative accuracy. And I have a big asterisk here because I don't want this to come across as a really harsh critique of these off-the-shelf force fields. It's an incredible achievement to develop them, but the reality is sometimes they're not good enough. And this is an example. So we have HFC-32 here, and if we look at vapor-liquid equilibrium for HFC-32 with GAF, what we see is that the results are pretty poor. So GAF is shown as the gray squares, and experiment is shown as the black crosses, and you can see for both the coexistence densities, the vapor pressure, and the enthalpy of vaporization, GAF just makes incorrect predictions. Now, these off-the-shelf force fields are widely distributed, the parameter sets are widely accessible, so unfortunately, these are too often the first choice and often the last choice that a simulator uses. People often don't go any further than just grabbing what's available, and that's understandable. It's not easy to do force field development. So what we want to do is we want to make methods that are fast and can improve upon general force fields for specific cases when you come across this type of a problem where you don't have a force field that's good enough. And the approach that we're going to take is we're going to get the bonded interactions and the partial charges as is from the generic force field of choice, or the off-the-shelf force field of your choice. And then we're going to apply top-down parameterization to the repulsion and dispersion parameters to try to improve upon those and improve our agreement with experiment. Now, the challenge of top-down force field optimization is shown here. So what we really want to do is we want to take some physical properties and we want to give those physical properties to a magical function which spits out the force field parameters and says, okay, here's the parameters you need. The problem is that in general, we don't have a good way to do this. So a few weeks back, we saw a presentation with the SAFT gamma me force field. And in that case, they have a nice mapping that can get you from physical properties to force field parameters. But in general, for all properties, for all types of models, this isn't something we can do. What we can do is we can go from force field parameters to physical properties by running a molecular simulation. Now, unfortunately, that's not necessarily very cheap. Especially if you're computing, a bulk thermodynamic or a bulk transport property, this could require a simulation that's a few nanoseconds long. So this is not a quick function evaluation, if you will. So the two challenges really that we see with regards to top-down force field parameterization is that evaluating a single parameter set can require hours to days of simulation. It's not easy. And oftentimes there's also multiple objectives or physical properties that you would like to target simultaneously. And we don't really want to apply arbitrary weights to different properties. So we'd like to be able to handle multiple objectives within a multi-objective optimization framework. So one solution to this is something called surrogate modeling. So I've taken this part from the last slide. So the idea here is right now what we do is we have force field parameters, call it this vector zeta, and we run a simulation, and that gives us some physical property y. And really the problem of top-down force field optimization is minimizing the difference between the experimental property and the simulated property by changing zeta, which is your force field parameters. And you can think about, crudely, you can think about the simulation being a function that evaluates zeta and returns your property. But this function is really expensive to evaluate, like I said. So what we're going to do is we're going to replace this expensive function evaluation with a cheap to evaluate surrogate model, which also maps from the force field parameter zeta to a predicted simulation output. So effectively what the surrogate model does is predicts what the simulation would give if we ran the simulation without ever running the simulation. And we're going to do this with Gaussian process models and support vector machines. So we're going to use these black box surrogate models to quickly estimate the expected simulation result without ever doing the simulation. And the benefit of this approach is that it enables a near exhaustive search of parameter space. And it also happens to make it easy to apply tools for multi-objective optimization. So it kind of solves the multi-objective problem as well. So the workflow that we have looks like this. What we do is we start out, we generate some initial force fields that we want to test, some initial parameter sets. We run molecular simulations with those force fields. We calculate the properties we're interested in. We then train a surrogate model to predict the property from the force field parameters. And this is an example of this over here. So here on the x-axis, we have the simulated property value. On the y-axis, we have the prediction from the surrogate model. And you can see almost all the points fall right across the y equals x line. The blue points are points that we use to train the surrogate model or fit the surrogate model. And the red points are points that we did not include in the fitting process, but show that the surrogate model is generalizing quite well to points that were not included in the fitting. Once we have a surrogate model that can predict the result of our simulation, what we do is we evaluate that surrogate model for a large number of trial force field parameters. So we're talking order of 1 million different sets of force field parameters. For each set of force field parameters, we predict the simulation output. And then once we've predicted the simulation output, we can basically select the parameter sets that best reproduce experiments. So if we have only a single objective to optimize, this is just whichever parameter sets are closest to experiments. In the multi-objective case, we can use this idea of a non-dominated set or a Pareto set. And so basically the idea here is if we have two objectives, objective 1 and objective 2, we want both of these to be as close as possible to 0. If we have a whole bunch of points here, the ones that are on this non-dominated front here are the points where you cannot improve in one objective without getting worse in the other objective. So these points are really all equally good. Unless you apply some weighting to objective 1 or objective 2, there's no way to say that one of those points is better than the other. So this is the approach we're going to take when we have multiple objectives. So for an example here, I'm going to show how we do this with HFC-32 and HFC-125 for vapor-liquid equilibrium. I don't want to spend a whole bunch of time on the motivation, but this R410A is a common refrigerant that's a mixture of these two molecules. We'd like to be able to do this separation, and there's a project we have where we're working on separation techniques. Our strategy here, we're going to take the intramolecular parameters and charges from GAF, and all we're going to do is optimize the LJ, sigma, and epsilon. To give you an idea of the problem size, we have 6 parameters we're optimizing for HFC-32 and 10 for HFC-125. We're going to do this optimization in 2 stages. In the first stage, we're going to optimize to get the liquid density correct at the saturation pressure. The reason we do this first is because we can do this with molecular dynamics, and that's a lot less computationally expensive. And then in the second stage, we're going to optimize for saturated liquid density, vapor pressure, and enthalpy of vaporization. So here we're using Gibbs ensemble Monte Carlo. So let's see how it works. So we start out, we get 200 parameter sets from a Latin hypercube sample. So you can think of this as a space-filling random sample. For each parameter set, we run NPT molecular dynamics at a set of 5 temperatures. And this is what we see. So the way to read this plot, on the x-axis, you're looking at the mean absolute % error in the liquid density. So just think error. And on the y-axis, you're looking at the number of parameter sets that have less than or equal to some value of the error. So you can think of this as being like a cumulative distribution function. So what you can say is you can say, well, we've got 25 parameter sets that have under, let's see, 40 mean absolute percent error. That's the way to read this. So this initial set of parameters, which came from the Latin hypercube sample, is quite poor, right? I mean, we hardly have what, like maybe not even 10 parameter sets that have under 10% error in the density. That's really bad. But we then take this data that we collected and we use it to train the surrogate model to predict the liquid density from the temperature and from the force field parameters. We then generate 1 million prospective sets of force field parameters. For each of those, we predict the liquid density with our surrogate model, and we pick the best 200 out of those. And this is what our next round of MD simulations looks like. Now we have, if you look at the inset here, we have 100 parameter sets that have under 2% mean absolute percent error. So this is extremely good. And this is a massive improvement. And this shows you really how accurate the surrogate models that we're using are. So we can do a couple more iterations of this. We get a little bit more improvement, but the takeaway from this is that we're able to generate several hundred different parameter sets that are all giving very low values for the liquid density or error in the liquid density. So now for the second stage, what we're going to do is we're going to start out with 25 parameter sets that we got from our liquid density screening, and we're going to use Gibbs ensemble Monte Carlo at these temperatures. And then instead of having one surrogate model, we now have 4 different surrogate models, one for each of these properties that we're interested in. And once again, we generate a bunch of new parameter sets, predict the properties with the surrogate models, and then this time now we select the 25 parameter sets from the non-dominated front. So if you remember, I was showing you that front here earlier when you have multi-objective optimization. So that's how we're going to pick the sets for the next iteration. And when you look at the results, here we have the results for each property. The different colors are the different iterations. And for every property you see here, we see improvement going from iteration 1 to iteration 2 to iteration 3. So up and to the left is improvement because that means you're getting more parameter sets with lower values of the mean absolute percent error for that property. Also, I'll point out we're getting the critical temperature and critical density. Those are improving even though we're not actually explicitly including those in our parameterization framework. By the end of 3 iterations of this, we're able to get 4 different sets of parameters that have less than 1.5% error in all 4 VLE properties simultaneously. So these models are quite good. We're very happy with them. Comparing them with what exists in the literature. So once again, black X's are experiment, GAF is the gray squares. I've added work of Rabe, who has developed an R32 or HFC-32 force field previously. And you can see from where we started with GAF to where we end with the red points, we have basically perfect agreement with experiment, and we have slightly better performance than the custom HFC-32 force field that existed in the literature. So we're quite happy with this. One more time, I want to point out we're getting critical predictions quite well as well. So here I'm only showing a single parameter set. I've been telling you how we're getting lots of good parameter sets. So let's look at what all of those look like. So now what I'm going to do is I'm going to show you all the parameter sets that we have that are non-dominated. So all of the parameter sets that lie on the non-dominated front. And we have 26 of them. So on this plot here, there are actually 26 different sets of colored circles. So there's different colors, 26 different colors. They're all circles, and they all fall on top of each other to the point that it just looks like this little blob here that I'm showing. So those are our 26 different non-dominated parameter sets, all of which are getting excellent coexistence properties. And if you look at the vapor pressure or the enthalpy of vaporization, once again, all 26 parameter sets are performing quite well. So the next obvious question is to say, you're telling me you have 26 different parameter sets. Are these really different force field parameters, or are they just, a very small decimal apart? And the answer is no, they're actually different. So here what I'm showing is the values of the sigma and the epsilons. And the way to read this plot is to follow one colored line. So pick one of the bold ones to make it easy. Pick the red bold one. And if you follow that line to where it intersects each axis, that tells you the value of the force field parameter that's listed on that axis. And what you can see is that of these non-dominated parameter sets, there's about 0.3 angstroms variation in sigma and 10 to 15 Kelvin variation in epsilon. So these do appear to be actually be slightly different parameter sets, all of which yield extremely good performance. So what did we do? So in summary, we ran 9,000 molecular simulations to do this, 8,000 NPT molecular dynamics simulations, and 1,000 Gibbs ensemble Monte Carlo simulations. But we ran 100 million surrogate model evaluations. So that's 100 million simulations that we did not run because we used the surrogate model instead. We evaluated a total of 7 million parameter sets, and in total, this took a few weeks to do. I won't go into the details, but the same procedure was very effective for HFC-125. Here I'm showing all the non-dominated parameter sets. We have 46 non-dominated parameter sets, and of those we had 4 parameter sets that had less than 2.5% error in all 4 properties. So this worked quite well. So in conclusion, I hope I've shown you that the surrogate-assisted optimization is a promising route for top-down force field parameterization in atomistic molecular simulations. One thing we really like about this approach is it maintains the well-tested and physically interpretable functional forms that we've been using for a long time. This is not a machine learning force field. What we're using machine learning for here is to guide the parameter search to help us identify good parameters for analytical functional forms. Our approach has been to take the intermolecular parameters and charges as is and just focus our optimization efforts on the intermolecular LJ parameters, but that's not the only way to do this. You could certainly toy around with, for example, including the charges in the parameterization if you wanted. And we were able to use this to develop highly accurate force fields for HFC-32 and HFC-125. And I didn't have time to show it here today, but we've also demonstrated that this approach can optimize Lennard-Jones parameters for trying to simulate solid ammonium perchlorate. So it's a very different system. It's a solid system, and the objective functions that you have look very different than in the case of vapor-liquid equilibrium. So we really think this is a pretty general approach that can be used for top-down force field tuning, and we're pretty excited about it. So with that, I'll go ahead and wrap up. I think I've finished in a reasonable amount of time. I'd like to acknowledge our collaborators one more time, my advisor, of course, funding, and the entire research group. This was from pre-pandemic times. I'm really hoping that we can get back and have another picture like that soon. And with that, thank you for your time, and I'll be happy to take any questions.
Thank you, Dr. Ryan. It was a pleasure to have you. I'm sure that was a really useful and practical presentation. So now we are open for questions. If you want to ask one, please enable your microphone or write down at the chat, and we'll read it. The people that are watching us from the YouTube can also write down the chat and we can read the question. Please feel free to ask.
May I ask a question?
Sure, Professor.
Hello, Ryan. Very nice presentation.
Hello. Thank you.
Thank you very much for that. Yeah, I have a couple of questions, but I'll try to focus
Bruno,
on. Yeah.
Can you turn on your camera, please?
No, not from here. Sorry.
Oh. Okay, no problem. No problem.
No,
go ahead.
I had to switch computer actually during the presentation, so.
No problem. No problem. Go ahead.
But yeah, so thank you very much for that presentation. It was very nice. My question is more on the philosophical side of this idea of parameterizing using machine learning, which I think is a very good idea, by the way. But the question is, you have parameterized quite a number of parameters for a very specific system. You have 2 molecules, right? And in my view, this will be a very good force field for these 2 molecules. But you kind of sacrifice a lot of the transferability of these parameters when you do such a specific parameterization, right? Do you think
Yes.
it would be a good approach for a general force field design to have machine learning more or less the same way as you applied, but for a very large scope of molecules? I mean, more molecules than parameters, more properties than parameters. What's your take on that? What's your view on that? Thank you.
Yeah. No, very, very interesting question. So I'll answer it in a couple different ways. So I agree. In this case, we have a fair number of parameters and fewer properties in single molecules, and this is why you see that we have as many different parameterizations, or at least part of the reason that you see as many different parameterizations as you do. With regards to transferability, this is an interesting question that we've considered. One thing we've considered is, say I want to take the parameters I've developed and I want to use them with an ionic liquid that uses GAF. How should I pick the parameters that I would use? And one thing I could argue is there's ways you could look at a distance in parameter space between the custom parameterization and GAF. And then if you wanted the most transferable molecule, perhaps you could pick the optimized parameters that were closest in parameter space to the original GAF parameters, with the hope that that would mean that would give you transferability with mixing it with an existing force field. More broadly, to your question about parameterizing, these larger force fields with this approach, I think that would be super interesting to see. I'm not so sure I'm optimistic that we're going to be able to get force fields that cover all of chemical space with a high degree of accuracy and transferability, but I do see room to develop force fields for entire class of compounds. So, instead of just one or two molecules, what about, all HFCs or something like that? I think that really might be the sweet spot going forward. And I think this sort of approach could certainly be used to do that.
Thank you.
Thank you, Professor. I think Professor Richard has some questions. You want to ask them, Professor?
Just a second. I gotta turn things on here. Oh, there. Here we go. Okay, so yeah, I posted them in the chat. I was having a little trouble with the last couple questions, but I think maybe you kind of answered those already as a part of the transferability issue. The last question there just says, is off the shelf? Is that the same thing as transferable? Is that what you were meaning?
Off the shelf is my way of referring to like these big, what I would consider like big basket force fields that are designed to cover large swaths of chemical space that the parameters are widely published for. So I think of like GAF, OPLS, all atom, TRAP. These are the force fields that are kind of off the shelf. Your starting point. When you have a new system and you just need to start somewhere, where are you going to go and grab? That's kind of what I'm referring to as off the shelf.
So they sound like they're transferable to me. Is the basic concept.
Yeah, the goal certainly the goal of them would be to be transferable across large swaths of chemical space. Yes.
Yeah. So then there's this customizable, which is what your approach has been so far. So you've
Yes.
customized force fields for specific molecules. And then,
yes.
So when you make the generalization to a transferable force field, if you, the way to do that and not get 26 different parameter sets is to put 50 or 100 molecules of that type in your regression, right? And so if you've got 50 molecules and they have to have, you have to recognize that a CH2 may appear in many different types of scenarios, right? And so it could be attached to a benzene ring, or it could be just a straight aliphatic CH2. And you've got to figure out, are those two different parameter sets that are necessary or not? Okay, so you're starting to get some idea of how big this problem is. You've got to have 50 to 100 molecules in there, several of the different molecules sampling that particular molecular environment enough to be able to distinguish if they're the same or they're different. And so now you're saying it's taking a few weeks to do one single customized force field for one molecule. And I'm saying, well, you've got to do that probably 100 times for 100 molecules all at the same time to actually infer which parameter set out of those 26 is going to be the best. That's so a few weeks times 100 times 100 is a big number.
Yeah, absolutely. I don't think, at least in my head, I don't think this approach today is something that you're going to just take and slap on, a whole transferable force field that covers a massive amount of chemical space. But I think interesting next steps are thinking about, smaller classes of molecules and thinking about then, questions like you were posing there. How do you pick what your different atom types are, right? So there ought to be smart statistical ways that we can look at whether or not you need to define a different atom type here, or whether that can get rolled in because there's excess information there and it can get shared with something else. So I think I think looking at classes of molecules is kind of going to be the next step. I'm not going to go out and build yourself a new transferable force field for all of chemical space tomorrow. That's definitely not in the cards.
Well, I don't know. I think it's it can be done, but might not. It needs some more thought, I think. But I think we're close to that.
May I step in again in the discussion?
Oh, sure.
Yeah.
So sorry to interrupt you, Richard. It's just something that's related to your question. I have a follow-up question on that. Let's say that you want to make a force field for the alkane situation, right? You have basically 3 atom types. You have CH3, CH2, and CH. It's a united atom model, let's put it that way. And then you have a set of molecules that you want to optimize for all the target properties that you have shown in the alkane case before. All right. How many surrogate models do you have to build? Is one for each molecule, for each property, or you can build something more collective that you can try to estimate simultaneously for multiple molecules and multiple properties? What's your idea on that?
So off the top of my head, I would be thinking to do the surrogate models aren't terribly expensive to build and train. That they're pretty cheap and evaluate. So I would be thinking about building a surrogate model per molecule per property. But I will say in the other system I didn't show, in the ammonium perchlorate system, we showed that you could combine several different properties together and have your surrogate model basically be a surrogate for your objective function, which was a combination of multiple different properties. And that also worked. So that would suggest that you can think about combining at least multiple different properties together, or perhaps multiple different molecules together into single surrogate models. I think that would be an approach that would be fruitful. I kind of like this. It's very, how do I say it, aesthetically pleasing to me to have a surrogate model that basically predicts a property that you would get from an MD simulation. That one-to-one mapping has some like aesthetical level of pleasure to me, but it may not be the best approach going forward.
Yeah, but with that, you have the combinatorial explosion that Richard was mentioning, right? Because you would have to simulate all the different simulations to predict all the properties for each molecule in order to train the individual surrogate models. But if you would have a way to train a single surrogate model, and based on, let's say, random simulations of alkanes that you would sample over, like, let's say that you want to, the maximum number of simulations you want to do is like 10,000. So you are going to sample from systems and properties, and you're going to feed this model with this 10,000 simulation data, and then you would have a much lower number of simulations to perform, and would avoid the combinatorial explosion. Of course, there is something you are sacrificing with that, but I think this idea at least could be put in practice for a large scale experiment, for trying to develop a whole force field for alkanes, for instance. What do you think?
Mm-hmm. Yeah, no, I think these are very interesting ideas. I've just, I'm just starting to think about how I would go about it for larger classes of molecules. So, you're kind of hearing the forefront of my thinking, and yeah, I think that's an interesting thought that's worth pursuing.
Just as a follow-up to that, I think it's one of these questions down here. Are you enforcing thermodynamic consistency between your surrogate models? But what I heard is no.
No.
Okay. Okay.
None whatsoever. That's something that you could think about adding. That certainly, you know, anything like that helps.
So the first couple questions were kind of detailed questions about Cassandra. I don't know if can you see those in the chat, or would you
Yeah,
like to
I can. So no, we don't have this capabilities for discontinuous potentials. So no, and no. And then regarding MoSDeF, yeah, so MoSDeF has been under active development. The really, for Fourier, the benefit in my view is that you can build, you know, custom XML files. So, you know, if you have a custom force field that you're using, you can build an XML file for that, and then you can distribute that. They have reasonable support for OPLS all atom right now. I've added some support for GAF, but GAF is really tricky because the charges come from RESP. I'm currently working on a partial charge module that will kind of integrate that more nicely. And then there is some support for TRAP as well. Let's see.
Yeah, there was some support for TRAP when I looked at it a while ago, and you know, I can run lamps and I can run GROMAX, but I didn't get anything out of MoSDeF with TRAP. So no progress then on either TRAP or even Potthoff's force field or TAMI. Is that right? Is that the current status?
Yeah, I don't think that those are built in natively. Again, you know, the goal of Fourier was not necessarily to have, it's not necessarily supposed to be a giant library of force fields. It's designed to be this atom typing engine that allows you to distribute and then apply force field parameters for smaller cases as well as the larger cases. But yeah, if you don't hesitate to post on the developer community is pretty active. Some of the documentation, and I'll need to go and do some of this at some point, needs some work, but don't hesitate to post on the GitHub. That you'll get a response from the developers.
Yeah. Okay. Well, I'll just put it out there. The workflow for a chemical engineer, like somebody who reads this book I'm working on, The Properties of Gases and Liquids, if you've heard of it, it's just think of that, or Perry's Chemical Engineering Handbook. Okay. Their workflow is go to chemspider.com, right click, download the mol file, feed it to the program, and get the property that you want. That's their workflow. So it sounded like MoSDeF had some promise to be that, but it's not. In 3 years, it hasn't gotten there. It's made zero progress.
Yeah, I mean, it's a big project. We're working on it. If you have, you know, post on GitHub, and we'll try to work out and see if we can get it to support the functionality that you want.
Okay, thanks.
Ajimiro.
Yes, please.
Okay. Good afternoon, everybody. Hi, thanks, Hi, for this nice presentation, nice introduction that you have done also in this presentation. When I first read the title of the presentation, I was expecting something like what Bruno has mentioned about the workflow, also that Richard has mentioned. But actually, when you already have a good model, a good force field model, and do this surrogate modeling for proper prediction, product design, and so on. But actually what you did was to try to fit a good force field based on experimental data and so on. And my question is about what kind, I think I missed some slide, I don't know if I said that, but what kind of surrogate model that did you use for that? And also, what was those multi-objective function that you have used in this parameter estimation that you did in the Atomistic model? And if you have checked for overfitting of this parameter when you do the surrogate modeling approach.
Okay, so I'll start from the beginning. So we used Gaussian process models, Gaussian process regression. In addition to, we also actually used some SVM classifiers to help with some areas where the Gaussian process models were doing poorly. So we kind of overlapped those two techniques. Then for so when we had multiple objectives, so this was the case of, let me go back in my slides. So multiple objectives was when we were thinking about having vapor-liquid equilibrium. So we have 4 objectives here. So we have the saturated liquid and vapor density, the vapor pressure, and the enthalpy of vaporization. And the way we handle this is and this is just an example in a 2 objective case. But what we do is once we evaluate all 4 surrogate models, then what we can do is we can compute for each property a mean absolute % error. And that's the objective for each property. So if you imagine we just have 2 objectives here, then what we can do is we can identify the set of points that are non-dominated. So these are the points at the front, at the Pareto front here, where if you want to see improvement in any one objective, you would have to sacrifice in another objective. And so we pick from those points. So we normally end up with more non-dominated points than we want to run simulations. So then we subsample from those points with a distance criterion. So our goal is, well, there's no point in simulating two points that are really, really close in parameter space. So let's try to space things out and subsample from those.
And what about the overfitting?
So sorry, can you repeat the last part of your question? There's a lot there.
Possible overfitting of your surrogate model.
So we didn't actually look into anything other than Gaussian process models, frankly. We tried several different kernels with the GP models and all performed quite similarly. They perform so well that frankly, we didn't look elsewhere. Let me to give you an idea of kind of like what this looks like here. Because I know everyone's probably a little bit like, oh, this is hard to visualize. So here's an example here. So what we're looking at, so the GP models have the input is the parameters and temperature. So here what we're looking at is a slice across temperature space. So everything in this slice is the same set of force field parameters. And then, so if you look at this first one, what we're looking at is the predicted liquid density versus temperature. And these predictions are from 3 different kernels with GP models. The black points are points that were training points that are used to fit the model, and then the red points are testing points. So these were not included in the fitting process. The shaded regions that you start to see in some places is the estimated variance. So the kind of the uncertainty in the GP prediction. But the overall takeaway here is that these did extraordinarily well, and frankly, we were trying to solve a problem, and we didn't look a lot further than that.
Okay, thanks.
Mm-hmm.
So thank you. Do we have any more questions? No, so our time is almost over, and it's time to wrap it up. I want to thank everyone for this discussion, and once again, thank you, Dr. DeFever, for the presentation. We were really glad to have you here.